Hey guys, I'm so stoked you're all here. You're just in time for a really sweet problem on the equilibrium of forces. Today, we're going to be looking at force equilibrium in a drive shaft. Let's explain some things before we start. First, what does a drive shaft actually look like? In its simplest form, a drive shaft is just a plain old rod that's really useful for transmitting torque. So in this case, our shaft is just a long cylinder with a single gear attached to it, though we're showing it without teeth here for simplicity's sake. Like this pretty much. Like so often, we've got to think about supports here as well. We'll put in a simplified version of a fixed support on the left and one of a movable support on the right. In real life, something called a deep groove ball bearing is also used with a drive shaft like this one. But for our purposes, these funny little triangles are a lot easier to work with. Finally, it's important for us to know what kind of gear we're looking at here. Let's just say that what we have here is a helical gear, since we can also use it to exert an axial force. Let's end by simplifying the shaft and cutting away the supports. The shaft itself becomes just a long line, and we can also draw the gear as a simple vertical line. Now we'll just cut away the supports and show only those forces that are being exerted on the gear. We're almost ready to go now. All we need now are some dimensions, and here they are. Okay, so we've got our problem to where it's straightforward enough for us to start working it out. Let's say the manufacturer has let us know the maximum forces that the supports can withstand. Of course, we want to know the maximum power of the forces we can transmit, so we're looking for the greatest possible radial and axial forces that can drive the gear from above. To find it, we just establish equilibrium in the x direction and the y direction. We add together all the forces in the x direction and get ax plus fa equals 0. Solving for fa, we just get minus ax. And ax, as you remember, was 500 Newton. Ha! It's a negative sign, which means we put the axial force in wrong. This would be correct. Now hurry up and calculate the radial force, Fr. We add together all the forces again and solve for Fr. This is easy enough, so let's add another little problem on top of this one. This time, we've been given an axial force and a radial force, and we're supposed to calculate the support reactions that result. The equilibrium of the forces in the x direction works pretty much the same as before, except in this case, Fa is negative. Now things get a bit more interesting with the y parts. Force equilibrium gives us this equation here. But we also have two unknown variables, so we're going to need one more equation. The solution is simply the equilibrium of the torques. So let's just establish torque equilibrium for the fixed support A. The support reaction forces of A go throughout our pivot point, which means they don't factor into the equilibrium here. For the other forces, we're looking at direction of rotation and vertical distance, and we get this equation. The only thing that's unknown here is By, so let's solve for By. Move the two parts being added over to the other side and divide their sum by the length of the lever of By. Easy peasy! We get a value of 475 Newton for By, and now we can get back to the equilibrium of the forces we were just dealing with. Now all we have is one unknown variable, so it's super easy to solve the equation. This means that Ay is simply 1,225 Newton. That went well. It could have been harder. Here's a little tip to end this with. We could have also established equilibrium of torques using the movable support. The cool thing about torque equilibrium is the remarkable fact that all forces that go through the pivot point don't count. But keep doing the problems we give you, and this stuff will become routine for you. Of course, it would suck if you picked the wrong pivot point on the test and have to spend the next 15 minutes solving a bunch of equations like an idiot. Otherwise, we hope you had fun today, and you've got to admit that it's pretty cool how easy it is to figure this stuff out. Maybe now you can go and swipe your neighbor's Porsche and take apart the transmission. Then again, maybe it would be smarter to just go ahead and try and tackle some of our practice problems. Alright kids, take care and have at it.